Okay, so we're going to start the next section. We're going to continue talking about finding the zeros for a polynomial function. The only difference in this section versus the last section is that we're going to add in the idea of having our zeros be imaginary, or in other words, having an I, or possibly irrational. Okay, so we're going to begin this problem with the same method that we've used on all of our other examples. So we're going to begin with our rational zero theorem. Which, remember, means that you are going to identify a P and a Q in your problem. So the P is going to be this negative 18, and the Q is going to be the number in front of the highest power, which will be 3. So we know that P is negative 18, and we know that Q is 3. So we're then going to write out factors, numbers that would multiply together to give me negative 18 and positive 3. So for 18, I could do 1 times 18. Or I could do 2 times 9. Or I could do 3 times 6. For the positive 3, I could do 1 times 3. All right, and then we're going to do P over Q, and that's going to give us our list of potentials. So I'm going to first take all of these numbers, and I'm going to put them over 1, which isn't really going to change anything. So we'll still have 1, 2, 3, 6, 9, and 18. Okay, and then I'm going to take all of those p-values and put them over 3. So 1 over 3 is going to be 1/3. 2 over 3 will be 2/3. And the rest of the numbers will simplify to numbers that we already have. For example, 3 over 3 is 1, 6 over 3 is 2, 9 over 3 is 3, 18 over 3 is 6. All right, so remember that this is your list of potential or possible rational zeros, which means that if the function has a rational zero, that it is going to be one of those numbers in the list. All right, so the next thing that we want to do is we want to pick one of those numbers in the list, and we want to check it by synthetic division to see if it's actually a zero. Now remember, we talked in the last presentation about if you have a graphing calculator, you can graph the function and take a look at what that function looks like, and at that point make some educated guesses. So I'm just going to really quick, I've got it graphed on my calculator, but I'm just really going to quickly just sketch it right here so that we have it to look at. All right, so it looks like on my calculator that this graph goes through that point and then kind of turns around and comes up like that. All right, so if that is my graph, then I can look at that and say to myself that negative 2, it looks like an x-intercept. So that's where I'm going to begin. I'm going to check negative 2. And remember, we check it by using synthetic division. So we divide into the coefficients in the original problem. So 3, 5, 25, 45, and negative 18. So we're going to drop our 3 down, and we're going to multiply. Negative 2 times 3 is going to give me negative 6, and we'll add. Negative 2 times negative 1 gives me 2, and we'll add. Negative 2 times 27 gives me negative 54, and we'll add. Negative 2 times negative 9 gives me 18, and we'll add. So because we got a 0 at the end, we know that negative 2 is a 0 of the function. All right, now I'm going to try one more. So it also looks like the graph crosses somewhere between 0 and 1. So if I look at my list, the numbers between 0 and 1, I have 1/3 and I have 2/3. So I'm just going to try one of them. I may have to go back and try the other one. I'm going to start with 1/3. And remember that we're going to plug in for our synthetic division into this expression where we left off. All right, so I've got 3, negative 1, 27, negative 9. And we'll drop the 3 down. We're hoping for a 0 at the end here. So 1/3 of 3, you can do that in your calculator. 1/3 times 3 is 1, and that's going to give you 0 when you add. 1/3 times 0 is still 0. When we add, we get 27. 1/3 times 27, again in your calculator, is going to give you a positive 9. Add and we get 0. Okay, so this is great. We now have 2 of the 4 zeros that we were expecting. Remember, our degree is 4, so we were expecting 4 zeros. All right, I have 2 of them. So let's go ahead now and let's take the problem and let's put the x's back into this. So we started with an x to the 4th. The first time through on the synthetic gives you an x to the 3rd. The next one's going to give you x squared. So this thing is going to be 3x squared plus 0x plus 27. Or I'm going to drop that middle term. So 3x squared plus 27. All right, and that is what we want to solve. We want to find that places where that is equal to 0. So I'm going to subtract the 27 from both sides of the expression. So that's going to give me 3x squared is equal to negative 27. I'm then going to divide both sides by 3. So that's going to give me x squared is equal to negative 9. All right, and then if I take the square root of both sides of that expression, I get x is equal to positive or negative. We know the square root of 9 is 3, and because there's a negative inside, remember that we'll put an I to account for that negative. So we now have all 4 of our zeros, right? So I'm going to just come over here and kind of make a list of those zeros. So we have x is equal to negative 2. We have x is equal to 1/3. We have x is equal to 3i. We have x is equal to negative 3i. So those are the zeros for the function. And then the problem will actually probably ask you to factor it as well. And so we'll want to factor that expression completely. All right, so I'm going to just come back up to the top here and get it factored. All right, so I'm going to write a factor for each 0 that I have. So my first 0 is negative 2. So the factor is going to be x plus 2. My next 0 is 1/3. So that's going to be x minus 1/3. And my next 2 zeros, because they're irrational, I have a couple of options. I can either write x minus 3i and x plus 3i, or I can actually come back here and use this as my factor. So 3x squared plus 27. Okay, and then there are a couple of things I would want to do with this. First of all, I want to work on the x minus 1/3 factor. We typically don't leave fractions inside the factors. So if I'm looking at x minus 1/3, and because that denominator is a 3, if I multiply both parts by 3, I get 3x minus 1. So 3x minus 1 is a better version of that same factor. It would still give you the 1/3 as a solution, but it takes the fraction out. So I'm going to do 3x minus 1 right here. On this second factor, the 3x squared plus 27, note that both of those are, you could pull a 3 out of that. So I'm actually going to like squeeze my 3 in right there. If I take it out, I get an x squared plus a 9. And then normally we're going to see a number like that 3 pulled to the front. All right, so I'm going to be looking at, for my final factored version, 3 times x plus 2 times 3x minus 1 times x squared plus 9. Okay, so we now have all 4 of our zeros and we have our function fully factored.